Welcome to lecture 11. In this lecture, we will draw the phasor diagram of synchronous generator once again, and we'll try to have some look at the armature reaction of this machine. Now, this phasor diagram we have drawn in the last class. Here we have assumed that this is the terminal voltage V and this is the I. This is the current that is drawn supplied by the machine, which is lagging the voltage. So accordingly, this is the drop in the resistance, this is the drop in the synchronous reactance XS. So if I add this voltage plus these two drop, I get this voltage, terminal voltage, sorry, the generated voltage EF. VT is my terminal voltage and EF is the generated voltage. Now then we said that in in lecture 9 we have seen that the EMF and the flux are perpendicular to each other, that is the induced EMF lags the flux by 90 degree. So if this is the voltage induced, then the flux that is causing this voltage is perpendicular to this. So this is the flux, this is the voltage, this is this voltage. Now here we are considering that the machine is having only the rotor flux. Then in last class we say that in the machine this is my rotor and this is my stator. Flux is produced by the rotor. Say I have a conductor here, say here it is dot, here it is cross. So how the flux lines are flowing? The flux lines are coming out of the rotor like this. They are going to the stator, making a closed loop through the stator and again coming back to the rotor like this. So this part is called the air gap of the machine. Generally this is of the range of 2 to 3 mm, at max 4 mm. So this is the air gap of the machine. This is my rotor, this is my stator. So the flux produced from the stator, from the rotor, here the rotor is the field, the flux produced by the field, which is the rotor, crosses the air gap and then comes to the stator. So if there is no current in the stator circuit, that is if the current is only in the rotor circuit, then the flux that is crossing the air gap is the rotor flux. So this is the flux phi f, which is caused by the field circuit only, that is due to the rotor field. Now let's say that the stator is having a conductor. Let's say that this is my stator conductor. This here the current is having a direction, say like this. So what does it indicate? It means that the flux lines are flowing like this. So this is another flux that is produced by the stator conductor. This flux is produced by the rotor conductor, and this flux is produced by the stator conductor. So what is the flux that is that flows through the air gap now? It is the vector sum of these two fluxes. So this is the flux produced by the rotor and this phi AR is the flux produced by the stator. This flux is known as the armature reaction flux, the flux produced by the armature current and the armature coil. Here when we talk about synchronous machine, the armature is the stator. So the vector sum of the rotor flux or the field flux and the stator flux or the armature flux is the net flux that is there in the air gap. So how we find this? Now what is flux? Flux is equal to mmf by reluctance. Now what is mmf? mmf is equal to N into I by reluctance. So when we are talking about armature reaction, that is the flux that is produced by the armature current, so this will be IA or armature current or this current that is flowing from the stator. So this is my armature current. If you look at this N and this reluctance R, these are some constant number. So the direction of the armature flux will be same as the direction of armature current. So this flux, that what we are calling as armature flux, is in same direction as Ia. So this is field flux. How we find the direction of field flux? Field flux should be perpendicular to the induced EMF. So this is how we find field flux. Then we are drawing the armature flux. So how we are finding the armature flux? It is in the same direction as Ia. Since Ia is in this direction, phi AR will be in this direction. Now this plus this is equal to this. Now if you ask me how we find the magnitude of this we will discuss later. Today we are only talking about the direction. So the direction of phi f is in this direction. Direction of armature flux phi AR is in the direction of Ia. So it is in this direction. So the resultant of these two is phi R. This is in this direction. This phi R is the flux that is flowing through the air gap under the influence of both stator flux and rotor flux. If stator flux is not there, then this phi F will be equal to the air gap flux. When armature flux is there, it is the sum of these two. Let's look at this diagram. Here we have drawn the phasor diagram of synchronous generator once again. This is under the assumption that the current is leading the voltage. That is I, this is my V terminal voltage. This is the current that is flowing through the armature. The current is leading the voltage. Here we have drawn that the current is lagging the voltage. Here the current is leading the voltage. Here again we have drawn the phasor diagram. For this, first we have added the drop IaRa, then we have added with that Ia axis, so we got E. Perpendicular to E we have drawn phi f, and parallel to I we have drawn phi AR. So this plus this is the resultant flux. So for leading power factor, this will be the phasor diagram. Here, if this is the phasor diagram at unity power factor, that is when V and I are in same phase. This is V, this is I. So IaRa will be in the direction of I. So V plus IaRa. Ia axis will be perpendicular to V. So it will be in this direction. Sorry, perpendicular to I, it will be in this direction. So V plus IaRa plus Ia axis will give me E. Now this is my induced EMF E. Perpendicular to this E will be my phi F, and parallel to Ia will be my phi AR. So phi F plus phi AR is giving me phi R. Here this is the resultant flux, this is the armature reaction flux, this is the field flux. Here this is the field flux, this is the armature reaction flux, this is the resultant flux. Now if you look at this diagram, if you look at this T diagram, you will see that here, let's put it in this way. Here, under the influence of armature flux, the resultant flux has reduced in magnitude. So this type of armature reaction is called demagnetizing armature reaction. Demagnetizing armature reaction. Here, under the influence of armature flux, the resultant flux has increased in magnitude, so it is called magnetizing armature reaction. And here the magnitude has not changed, but the angle has changed, so it is called cross magnetization. Now here this is not purely demagnetization, it has a cross magnetizing component. What is the cross magnetizing component? This much is the cross magnetizing component, and this much is the demagnetizing component. So this armature reaction has both the component. It has a cross magnetizing component as well as a demagnetizing component. If you look at this, here also it has a cross magnetizing component of this much and a magnetizing component of this much. If you look here, it has a cross magnetizing component of this much and a demagnetizing. If you have to look it in this way, the field was initially this much, now the magnitude of field has reduced to this, so this much is the demagnetizing component and this much is the cross magnetizing component. Here if you look at, this much is the cross magnetizing component, this much is the demagnetizing component. If you look here, this much is the your cross magnetizing component and this much is your magnetizing component. So a armature reaction has two components. One is a cross magnetizing component, another is a demagnetizing component. So depending on the power factor of the current, the armature reaction can be cross magnetizing, can be demagnetizing, or magnetizing, demagnetizing, cross magnetizing, or any combination of these two. The phasor diagram that we have drawn today, all these things has both cross magnetizing and magnetizing or demagnetizing component. Here if you look at this much is the demagnetizing component, this much is the cross magnetizing component. If you look at here, this much is the cross magnetizing component, this much is the demagnetizing component. If you look here, this much is the cross magnetizing component and this much is the magnetizing component. We will further look into this armature reaction in the next class. Thank you.